Hello and welcome to Lost in a Light Field. And this is our first episode in 2026. And I'm Saskia
Hello, everyone.
Groenewegen, and with me is.
Alexander Meijers. Welcome, everyone. Indeed, our first in 2026. And today we have something really special.
For sure. We are super happy that it's here because our guest today is, drumroll, Nathan Matsuda, who's a research scientist at Meta, who works on computational camera and display systems for immersive visual technologies. Particularly on research around augmented and virtual reality.
Now,
Welcome.
let's bring him in.
Hi.
Hi, Nathan. We're
Hi.
super happy that you are joining us today.
Thanks for having me here. I'm very excited to chat today.
Yeah, so
Yes.
Nathan, you work on headset prototyping, right? That's our topic today, and you're gonna tell us a bit about your work.
Yeah, so I
That's
think
right.
I will basically give an overview of the last 10 years of work that I've done and that the team that I'm on has done. And I think the way that we'll do this is we'll basically just go through a slideshow of photos of the headsets with some other little explanatory material, but we'll keep things high level and talk about kind of the motivations behind the work and the types of choices that we make and the way that we actually go about doing this kind of research.
That sounds very interesting. I'm very interested in how do you build a headset and how do you get there, and maybe which crazy side ideas do you have along the way?
Yeah. And I think we'll keep it loose. You can jump in and we'll just talk about the subject as we go along throughout the presentation. So so let's get started.
Awesome.
So let me share your presentation.
Yeah. So we're going to be looking at a lot of photos like this. And these are all hardware devices that are in service of this goal of creating a sense of wonder for the viewer. And I'll explain what that means. And starting with sort of the personal story. So about a decade ago, I started as an intern at what was then called Oculus Research. And I saw this pre-release Rift demo that gave me the feeling of glimpsing something that I'd never seen before. In science fiction and cinema, this feeling is often called a sense of wonder. And I felt it very strongly, when I put on this headset for the first time, to an extent that I had really rarely felt in other mediums, not even in film. And yet it was very limited still in many ways. And so fittingly, what I was starting was working on a research team that was specifically tasked with unraveling some of these limitations that have existed with head-mounted displays. So among other topics, here are some of the ones that we have looked at. We've got resolution, we've got field of view, dynamic range, latency, accommodation, which is the eye's ability to focus, and comfort. We want all of these things so that we can see the content clearly, so that we can activate our peripheral vision in the way that we would in the natural world, so that we have the same brightness and contrast that our visual system expects to see in the real world. And then so that the focusing system of the eyes works in the way that we normally would, just so that everything is sort of working the way that it would be normally, so that it's not distracting. And then finally, it has to be comfortable. It has to be small and light enough so that the physical device itself also doesn't distract from this visual experiments. And we want all of these things, regardless of whether we're talking about augmented reality or mixed reality or virtual reality. We kind of need these no matter what we are looking at, so long as we're using our visual system to interact with the digital world. So I'll start by I'll illustrate a couple of these visually in the context of augmented reality glasses. So let's say we have this view. This is near my house in Seattle, looking out over a broad vista. And let's say that I pull up some sort of fictional virtual interface here. So the idea is that we want to have this, perfect unobstructed view of the real world. And the very first thing that we run into with waveguide based displays is that they have fixed focus. So if I'm focusing often to infinity, I'll see the display clearly. But in this case, I'm looking at my hand. The display content is supposed to be in front of my hand, but because I'm focused at infinity, or because the display is focused at infinity, it's blurry and I just can't read it. So we need to have some sort of ability to refocus, and that's a difficult problem across all HMDs, because it's a complicated optical system that you have to introduce one way or another, and it could even require something like holography, where you have wavelength scale control over the paths of the light through the headset. So it's a difficult problem. Now, the real world also contains a very broad range of luminances. The difference between like a bright cloud and the shadow on a tree can be 5 to 6 orders of magnitude difference in terms of brightness, in terms of the number of photons that are actually flowing into your eye. And so this is challenging, because you have to get all of that same amount of energy into your eye from the display side, which uses a lot of power. And you're fighting against any inefficiencies in the system, like a waveguide, which loses a lot of light as you pass through it. And if you don't do that, then when you're outdoors or even in a bright room, you just can't see what you're looking at. So it's, again, a fundamental problem. Now, AR, it's particularly hard, because even if you just make the image brighter, like I did there, you're adding it to the background image. So you have this very hard uphill battle where your contrast is a function of your display brightness, which you do control, and your background, which you don't control. And so you may actually need an additional system that layers a darkening, some sort of darkening capability behind the display, so that you can actually see it when you're outdoors in the bright area. This might be something like just a purely sunglasses layer that covers the whole field of view, or maybe it's a pixelated dimming layer that, like I've shown here, just kind of dims down roughly where you need to see the content. Or we can say, forget about AR, we're just going to do MR, where there's a camera image and you actually have full control over how the images are composited together. That's sort of one of these choices that you can make in these systems. And then finally, we want to be able to use the whole field of view. So in a waveguide display, you might have a very limited field of view, whereas with a pixelated dimming display, you can cover the whole field of view. And now you have this issue where the actual usable range of content is limited by the smallest field of view of all the systems that you have in your display. And if you're getting like driving instructions or something, and you need something to pop up over in the corner, you just won't be able to see it if it's outside of the field of view. So these are all very important aspects, and it's a very interesting list of things to work on. However, these are all technical challenges that I've listed here, and they aren't in themselves why I was drawn to this field and why I wanted to do this. So what I wanted to do.
Can I ask a question before you continue? Sorry to interrupt, but so you have this list of topics that where you're trying to basically reach like the capability of the human visual systems, and none of them are quite there yet, correct?
Yeah.
Correct. But looking at all of them, which of them do you think is like the furthest or the closest to human vision, and which one is still the furthest away?
Yeah. So where we are right now, we can, in a lab prototype, reach resolutions where you cannot distinguish, where if you incrementally change the resolution beyond that, you cannot distinguish it. So that's as much resolution as you need to get. We also have lab prototypes that can reach pretty much close to 100% of the human field of view. And if you actually
showed that graph last year, right?
Yes.
Had a huge field of view. That was pretty awesome.
So you've seen it, and it is possible with sort of a larger headset to actually get to the whole field of view. We have built a headset that has the dynamic range of, and this is all a preview of things that I'm going to talk about, but it's useful to summarize.
Oh, sorry.
No, it's useful to summarize here because against this list. So we've also built something that has the full dynamic range that you would expect to see in an indoor scene. We've built a headset that has imperceptibly low latency. We've built a headset that can address the full accommodation range, and we've built some devices that are pretty close to the weight of actual glasses. So individually, these are all achievable in a lab prototype. What is very hard is putting it all together, or even picking and choosing which combinations can go together effectively. So for example, field of view and resolution directly fight against each other because you have some number of pixels, and the further you spread them apart, the less resolution you have. The same thing goes with adding like comfort and accommodation. So accommodation usually requires some sort of mechanism to adjust the focus, which adds weight, and so that negatively impacts comfort. So what I would say is, from a component technology level, these all appear to be tractable problems. From a systems level, they may not be. I'll say maybe the dynamic range is the hardest one, because if you want to be able to match outdoor dynamic
Yeah, it's
range,
huge, right?
you
The
need just a
brightness.
crazy amount of power.
Yeah.
You the power of the sun in the headset, and that's not. But
So if you want to, so maybe, so when you talk about focus point, because if you have glasses, they have always one single focus point.
Yeah.
I've seen in the past, and I forgot which device it was, where they were able to have different focus points depending on where you were looking at. Where would that fit in one of these?
So that would be in accommodation. So accommodation not only, so the simplest version of this is essentially autofocus, where you just look to a single point and you refocus. But a more complicated one, which was actually the first project that I did in my internship that we'll talk about in a minute, does attempt to put different focuses at different parts of the image. Yeah,
it could be that I actually talking about that exactly that part. Maybe I've seen it somewhere, and I think it's really interesting but combining all these things has also an impact, because you, as you said, some things can't work together, but you also have, of course, a limitation on your compute power on the device itself.
Yes. As the working on a display systems group means that we in order to make progress on these topics, we intentionally ignore the compute questions almost always. And that's one of those strategic choices that when you're setting up a research roadmap is kind of necessary in order, because if you even in the same vein as if we tried to combine all of these at once, we also wouldn't have any, wouldn't be any moves to make. There'd be nowhere to go if we were trying to combine them all simultaneously. I agree. Strategically, we say, okay, we're going to ignore compute. Now we're going to ignore all of the other constraints except for resolution and just go down that way. And then we're going to ignore all the other constraints except for just field of view and go down that way. And as you probe out this map of possible component technologies, you eventually start to see, okay, well, now we can put these two together. And we can put these together, and eventually you want to get to something that the necessary condition for achieving this sort of seamless use of the human visual system requires all of these things, and some other things that are a little bit more subtle, like having high color gamut and things like that. But if we try to do it all at once, then it's just an insurmountable problem. Hence the breaking it up into smaller problems.
Yeah, that makes sense. Yeah, thanks.
Okay, so let's keep going. So I crossed all of these out because it's like, these are all important problems. We have to solve these. They're interesting problems. I would like to work on them, but they aren't the motivation for me. The motivation for me is I just want to see cool stuff. Like I want to experience the creations that artists all over the world have made. I want to provide for these artists a new medium that they can use to do things that they haven't done before, and they can, address the human visual system in a way, in whatever way that their art takes them. Like that's what I want. And so that the framing for me when I approach these individual subproblems is, how does it get me to the thing that I actually want? It's like, sure, here's the list, but it's like what the list really is it's just the same thing over and over again. I want to create a sense of wonder, right? So now with that framing, we can go through these individual projects and kind of talk about the technical side, and then how this arrow points to creating something that is cool for the human visual system. So I've kind of grouped, this is like approximately chronological order, but not exactly. But I've grouped it mainly in terms of like what topic we're talking about. So one of the first things I did was looking at field of view in augmented reality. So I rigged up this pretty rudimentary cave system where I had a projector and some tracked 3D shutter glasses. But instead of having a wall that it's projected on, or an LED wall or something, I used a theatrical scrim so that you can look through it out to the office that you're inside. And so we basically made we emulated an AR virtual desktop environment with shutter glasses and a projector, so that you could sit and use a computer, you could use a web browser, or look at a sort of a mock-up of some avatars, or in this case, just look at like an outline of what different fields of view looked like. And then in software, we can then crop the field of view of the actual rendered content to different ranges, and then just have a bunch of people sit down and use it during the day and say like, hey, is this enough? Is this enough? And what everyone quickly understood was that the 50 to 60 degree fields of view that were state of the art at the time for AR glasses were actually not enough to even hold a conversation with two people or use a desktop web browser. And so we were able to then tell the story and motivate the waveguide research teams and others, and people that are working on UI design and other groups to target higher fields of view as just a necessity. So that was a quick early project, and at the same time, basically currently with the project, I was also working on this problem of dynamic range in AR, where layering the content over something that's bright means you just lose visibility of the content, you lose legibility. So I started. These were some Loomis glasses, like from 10 years ago, early Loomis glasses, and I just took a transparency and I colored in, with a marker over part of the region of the display. But I put up a menu and I looked at it and I just colored it in behind it, and I did a bunch of little quick things like this just to see like, hey, if you just imagine that you had some sort of display that can darken behind it, is this even useful? Like, does it, it's going to be blurry because it's right in front of your face, but like, does it help? And I went through a series of these prototypes. This is like an iPad display that I like delaminated the backlight from. This was a little calculator display so that I could like walk around with it. This was another version of that one. I basically like threw a bunch of things together just to get really quick. This was over the course of like a month, just get a quick sense of like, what does this look like? And the conclusion was, it's not a great way to deal with dimming down the background, because you get these blurry outlines around the objects. You cannot get a perfect composite. But on the other hand, it makes it, you can actually see it. Like, the difference between not seeing something and seeing something is a big change, and that's probably worth it. And if you hand this to people, so like, this is my boss, so like I would grab people and be like, hey, put this on and like just toggle this on and off, and everybody's like, yeah, and like it's the difference between seeing it or not seeing it, and that's important. And you can kind of learn that level of detail with something that's just taped together, essentially, like a very basic prototype. And we went through all of this like very quickly, and then landed on the first sort of full up prototype that I did with our engineering team. And so this is sort of a component of the research that we do that I think is very important. We're lucky to have this professional engineers on our team that can really integrate the concepts that we prototype quickly into something that is much more complete. And that's an important enabler for the user experience side of things, or the user research side of things, where you can actually have a bunch of people pick something up, or you can run a bunch of demos and get a wider range of feedback from people than just me handing it to the person on the desk next to me. So this one here, I'm gonna use this format throughout the talk, where I here's the first for the sort of like finished headsets that we do. So this was the first one that I did when I started as a full-time employee, and I've listed the mechanical engineers there underneath, and we threw this together as a demo for internal events, where we wanted to have something that would, we had the strategy of we wanted to catch people's attention with something that looked unusual, so that we could get people to come and experience something that is relatively mundane. Like, if you just tell somebody, here's a demo of, we're going to show you some text and we're going to dim the background behind the text so you can read it, that doesn't sound super exciting. But if we wrap it into the holistic experience that includes the design of the actual prototype itself into something that excites people, that's like, oh, this is cool, this is something that I want to look at, then you can get a bunch of people to try it. And so we did this. This is Michael Abrash, who's the chief scientist at Reality Labs Research, looking at it during one of these demo days when you had a bunch of people coming through. And you can actually see there's like a little like chat window that's showing chat bubbles. You can't see the text because it's being shown through the Loomis waveguides that are on there, but you can see the dimming that happens on the LCD behind it. And that's really the how this prototype functions, even though it's pretty simple. And then finally, we went to a much more complicated version of this headset because we needed to know, the form factor of this is great. It's easy to like leave on a table and people can pick it up and try it. But the resolution and capabilities were really low. This just has a Raspberry Pi inside. So it's like running just a simple text thing. This is a full-fledged AR headset that I sourced some high resolution transparent LCD panels. Our mechanical engineer, Joel, fitted them to the front of a prior headset that some of my teammates had made based on a Rift, where they took a Rift and then, actually you can see it better in this view. So there's a Rift display, like a full Rift in there on the top, and then a pair of curved combiners to give you a Rift-based AR display. Wow. And then we added the dimming element on top of it there. And so this was like a fully fledged PC VR capable, like it looks like a Rift on the computer. And so then you can run, we used the Oculus Medium, it's like a painting app for the demo here. And we made an extension to it where if you paint a shape, the dimming LCDs also occlude the background behind it. And so you can kind of see this in this video here. So this is with the dimming on. So you can see that it is being composited, not perfectly, but visibly over the bright LCD. And then if I turn off the dimming element, so it's like tracked and everything, it's a normal Rift display. But if I turn off the dimming, then you see that loss of contrast that a pure AR display would have. And so this is sort of the first like fully interactive version of a dimming capable demo that we're aware of anyone doing. And it was certainly the first that we did to sort of evaluate the necessity of doing something like this in AR for really any environment. This is a pretty dim office environment where it's just the screen that's causing the loss of contrast. But you would certainly need something like this if you're outdoors. Okay, so that's the end of this first AR section. So let's pause now again in case you have any questions. Otherwise,
I have a question.
So many questions.
Yeah,
that's so cool. Also, it's like so. Yeah, no, sorry, Alexander, go.
Yeah, the demo you just show because I wanted to connect back to that one. You had you made it black on the behind what you were drawing.
Yeah,
but it's only black behind the part where you actually draw. So the rest is still transparent.
Yes,
because what I see a lot with current devices, take Snap Spectacles or other type of devices, take the old HoloLens, is that the whole display is dim.
Yeah,
which means if you go outside and you want to see good through the device, you actually need to dim very hard, which makes also the rest of your environment not good looking, to be honest, and even riskful. You want to introduce it, for example, within the field for industry examples.
Yeah.
So I really like the example where you just only are graying out behind what you're actually showing.
Yeah. It's like it reminds me of like a high dynamic range displays, right? Where you basically have a second layer to modulate the first layer.
Mm-hmm. Yeah, it is conceptually exactly the same as that, where your world is the backlight. You're dimming the backlight, and then you're well, I guess it's not exactly the same because you're rather than multiplying your next layer with that backlight layer, you're actually adding it to it. And that's the difference there. But in terms of the system architecture, it is very similar. It's just a dual layer display.
Yeah.
So that's cool. Layers depending on the backlight coming out. So if the backlight is harder or higher, it will actually dim more.
This first prototype didn't have any functionality like that, but conceptually what you would want to do is have some outward facing high dynamic range camera that understands what's bright or dark around you and then
Yeah.
contextually dims down as necessary to create the target contrast, so that it's aware of both the background and the target content, and then does the best possible thing that it has the capability to do, to match what the intended viewing condition is.
So how much of your job is like finding extremely creative ways to tape together like off-the-shelf components to come up with like new things?
That is a lot of the job. A lot of the job is how can we invent as little as possible and achieve the goals that we want. And that sort of sounds like we're trying to avoid inventing things, but I think it's actually an important it's an important way to discover new things, where you just say, all right, let's gather everything that works right now and put it together and see something as soon as possible, because then we'll get the most understanding of it. Of course, we also, we'll do literature reviews, we'll do simulations to testing out before we build stuff as well. But whenever possible, we try to build things as quickly as you can, because that's where you have the most rapid information gain. And then you can say, all right, here's a new way of doing it, or here's a combination that nobody's done before, or here's a workaround, or and for me personally, in this case, having done these two demos, that my takeaway from this was, I actually don't want to work on AR. The AR, the capabilities of AR for utilitarian purposes are great, and like I fully buy into the fact that they are very useful everyday devices, but they are unlikely to ever be an ideal tool for creating magical visual experiences, because of those two that I just described. It's like I did these two projects and I was like, wow, it's hard to create. It's nearly impossible to create a perfect composite between the virtual world and the real world in AR glasses. And that means that I probably shouldn't be working on this, because it doesn't move me in the direction of my goals.
And you have a background, before you became a researcher, you have a background in visual effects, right?
Mm-hmm. Yeah.
Like,
So
does that influence how you approach your work right now?
Oh, well? Absolutely. Yeah. For me, they aren't really separate things. The visual effects work that I did. So I was a compositing supervisor for about 5 years, and it's exactly the same thing. It's like we have some vision of what we want to see. We have some set of tools, and that includes like footage that we've captured or elements that we can pick up, and we need to put these things together to best create this end vision. That process is exactly the same as doing research into head-mounted displays. You have a bunch of tools, you have something that you want to see at the end of the day, you got to figure out how to put it together. So for me, it's one in the same, and a lot of the individual tools and skills that you use when you're a VFX artist are obviously different than when you're doing optics research, but the strategies are much more aligned. And so I take a lot of the actual problem-solving steps that I would take when I had to start fresh on a new shot, or like start a team working on a new shot, and then I take very much the same approach of breaking things down, making quick progress in the areas where you can make quick progress, and then looking at it as soon as possible. That's exactly the same thing whether you're doing VFX or this kind of head-mounted display research, in my experience.
Interesting. Yeah, very valuable then to have that background.
Yeah, I think it was good practice for doing the same kind of work at that strategic level. Cool. All right, so let's talk about mixed reality. So the conclusion that I had when I looked at these AR projects was, we really need to be able to control how the image is being formed in order to achieve the goals that I have. And so naturally, it would make more sense to then capture your real world view, have it digitally before you composite it, and then show it to the people that are using the headsets, rather than having this completely uncontrolled external environment that's just passing through optically. It's a much harder system to build. There are a lot of disadvantages if your goal is creating images with full control over them. The first mixed reality project actually was a bit of a tangent, though. This was the first thing after I made that choice. I was like, all right, I'm going to sit down and I'm just going to think for a while and play around with some stuff and decide what to do. This project actually happened kind of by accident, because what I was doing was I was using an early pass-through prototype for Quest before it came out. And I was just wearing it, and I was just walking around the office, just using the pass-through. I turned off all the UI stuff. I was just walking around to kind of get a sense of it. And what the thing that I noticed the most, I was expecting to be paying attention to things like latency and dynamic range and stuff like that. The thing that I noticed the most was I would start talking to people, and it was really weird because I could see them, but they couldn't see me, and it really like threw a wrench into any conversation. Like it was just made it impossible. So what I started doing was sticking eyes on the front of the headset. So for I drew them on. This was like, I got some like little OLED displays. I think these are OLED or LCD displays, I don't remember, from Adafruit. And I just cut off the front of the headset and I put it on. There's a bunch of tape you can see to hold it on there. This is just playing a loop animation from some project on GitHub that I found that draws eyes. And then eventually I started working up to an actual 3D display. So this was the first version of this one, which is, it's a Rift. It's actually two Rift S's that we took apart. One of them is the normal one that faces the viewer, and then the other one, the second Rift S, has the screen flipped around the other way. And I found these lenticular sheets that are from 3D movie posters. So it's like a big piece of plastic that has these cylinders molded into them, so that when you look at it from different angles, you get a different part of the poster behind it. And I just stuck this onto the Rift display, and it creates a simple light field display. So that when you look at it, you don't need 3D glasses or anything. You see a 3D image. And then this was like just a Unity model of my face. Actually, it wasn't even a model of my face. It was just a generic face model that we projected the texture of my face onto. And I would just walk around and be like, hey, and talk to people like this. And it was clear that of course it was weird. Like, it looks goofy, but what was immediately obvious is there was a step change in the way that people interacted with me. So when I had the headset with nothing on the front, there was this weird disconnect where people wouldn't engage, like they wouldn't make eye contact, they wouldn't engage. And as soon as you do this, people, even if they're like laughing or whatever, it's like they're looking at you, and now they're interacting with you in a way that they weren't before. And I was like, oh, this seems like something that we should work on. So
So let me ask the probably obvious question at this point. Like 10 years later, Apple has of course done this with the Vision Pro. Yeah. Why has Meta not gone down this road?
I will answer that question in a second.
Actually, to be honest, if I would think about this, I think I'm happy that they didn't do it, because it actually, I mean, even my kids, I have a Vision Pro here, and my kids, if they see my eyes going through it, they're like, they get afraid. It feels extremely scary.
Yeah. So I think, so we built this version. Yeah. And we spent a lot of time engineering the actual display module. So this is actually a very small VR headset. It was one of the smallest that had been built at the time. And the reason is, when we did the analysis on the light field displays, it's really, really important for the image quality of the light field display to have the content as close to the actual display plane as possible and not move it really far back. And so we published this at SIGGRAPH Asia. This is my presentation video of the fully working system there. And the conclusion in the paper is, and we did a user study that showed that in fact this does meaningfully change the ability of people to make eye contact and judge and also interpret where you are looking as the wearer. But it is critical that the resolution be higher than displays were capable of at the time, and that they be significantly thinner than the VR headsets were capable at the time for this, so that you don't have to shift the image too much. And so the conclusion was, this is something that will be an important component of glasses form factor mixed reality headsets, and you shouldn't do it yet, because there is a threshold at which and there's like a plot in the paper that shows like you have to reach this thickness and this resolution before this is actually worth doing. And so that was the conclusion that I shared. That's like this is an important thing to have on our in our sights for in the future, but it's not something that we should do at this time.
Is that kind of similar to what you see in gaming, that you see a lot of people want to show an avatar that
The
you
uncanny
can create
valley. Yeah.
and then at some point it gets to a point that it becomes more scary than it actually becomes human.
Yeah,
because
I mean that's a very subjective question that I think is difficult to target to specific specifications of the hardware. But even from a technical image quality standpoint, you still can't really do this effectively yet. And so what my recommendation would be is wait until the technical capabilities can produce sufficient image quality that you can actually get the social signal of where the eyes are looking, and then you have to address the uncanny valley question at that point. But even that question is in the future. It's just, this is not something to do yet. This is something that we want to have in our portfolio in case we want to use it in the future. But it is a research topic at this time.
But shouldn't displays have the resolution by now to make that possible? Like, what's the problem at this point?
You jointly have to have. So I don't remember off the top of my head what the target resolutions that I was proposing were. Micro LED, micro OLED displays currently have that. The sufficient resolution that you would need, but you also need the thickness of the overall headset to reduce. And then that's aside from the question that micro OLED is generally just cost prohibitive, period, especially for something like this that is not a core component of the system. Like the marginal cost of adding an external display has to be tiny in order to make it worthwhile. So and that's not, those are questions that we didn't even consider in the published paper, but it's like the system's cost of adding this, it has to be way lower than it would be possible right now before you would actually want to do it.
Yeah, the other thing, but that's what, for me, if I look at this, where you showed in the video, it feels more human because I see a lot of your face. So there's a very small glasses in front of your head.
Yep.
So even while you pull up your eyebrows, you actually saw your actual eyebrows going up.
Yeah.
If you take, for example, then the Vision Pro, where everything is obfuscated, you can't see anything except those two, shadow eyes. It is completely different from the experience you see in this video already.
Yeah. So I think that, and I showed this demo to a number of people. I think that it even at this level, which I don't think meets the minimum bar, just was enough to show people that it's promising at this level. So I guess we met the minimum bar as a proof of concept, but it's certainly far from the minimum bar of something that would actually work in a social situation. Okay, so now there's another piece of this puzzle that I kind of realized while I was working on this project. So, all right, we've got the external view. We can see people's eyes. Let's pretend that that's working perfectly. There's another thing that I need though, which is that they can judge. They have a perspective correct view of my eyes. They can judge where I'm looking, but my view of the world is still incorrect because the cameras aren't where my eyes are. They're out on the front of the headset. And for current headsets, it might be even like tens of centimeters in front of the headset. It might in front of my eyes. Like that's a pretty far shift. That's like moving your head like half the depth of your head forward, which can be disorienting, but also just make it hard to like grab stuff. Like it's sort of limits the functionality of the MR headset. So we started this what's now a whole series of headsets, kind of looking at this problem, and we did this in a pretty rapid clip. So the first version of this was we said okay, let's think outside of the box. If we want to move the headsets, the cameras back to where the eyes are, what's the simplest possible thing that you can do to get them back here? And what we arrived at was, well, you have to get around, the view can't be blocked by the headset, but we could put them out here and put them at the correct plane so that they're same plane as your eyes. And then now what we're going to do is we're just going to interpolate these images. So it's an interpolation along the line between the two views, which in theory at least is easier than extrapolating from views that are in the front of the headset. Like, just roughly speaking, interpolation is usually easier than extrapolation. So we had an intern, Sushoban, who developed a multi-plane imaging algorithm. This was pre-3DGS, pre-NERF, where I guess was it early NERF? I guess it was early NERF times. And we so we did this like relatively lightweight multi-plane rendering algorithm to move the views into the headset, and like it kind of worked. But the problem was we were working in the space where we'd made a headset that was never going to work from a form factor perspective, which again, like I talked about at the top, it's always worth going down the line of like ignoring all of your other constraints to solve one problem. But as soon as you've done that, then you have to take a step back, and it's like, well, we're not going to have this hammerhead shaped headset thing. So what else can we do? So fast forward a few years, we took another stab at how to do this without leaning on reprojection a bunch and inferring a bunch about the world. And my colleague Grace came up with this idea of doing a variation on a light field camera, where instead of capturing a 4-dimensional light field, you're actually using a micro lens array to capture a single view, but from a different position than the camera actually is. And so she designed this. She did this optical design where the individual lenses and the pupil that's behind the lenses are in a specific prescribed pattern, so that they in aggregate create a virtual pupil that's back at the nominal position of the viewer's eyes. And you can actually see this if you take one of these lens elements and look at it. It looks, and you like hold it up to a bright wall or something, you see this little hole that's where the pupil is, that's actually back behind where the physical thing is. That's like 35 millimeters back behind behind the actual device. And so you can have this sensor and lens array on the front of the headset and directly capture the view that you actually want. Of course, there's a little bit of stitching that you have to do, but there's no reprojection, which is the key part. The drawback here is that it adds a bunch of cost and complexity. Like, now you have a bunch of lenses, hundreds of lenses, you have these big sensors behind them. And now that we've shown that you can do this, now you have to ask the question of like, is it really worth it, or what is the perceptual impact of doing this? And so that's when we built this thing, which we call Camsicle, which is cameras on a stick. And this is a completely different way of dealing with this problem, which is that you stick a mirror on the front of the headset, and then you place the cameras looking back at the mirror so that their reflected positions is, again, exactly where your eyes are. This is even more unwieldy and fragile than the first one that we built, but it lets us run user studies, because unlike this one, which had a bunch of cables running off and it's high-powered compute thing, and there were other image artifacts that would be distracting to user study participants, like that's what they would talk about rather than the perspective. And this one was too big to be comfortable, so we ended up with this one, and then we eventually refined it into this one, which is Camsicle 2. And finally, we're able to run a bunch of user studies to test the effect of perspective offsets. Additionally, my colleague Eric implemented a low latency algorithm where each row of this camera is written to each row of the display, one right after another. So instead of having to wait for an entire frame from the camera and then displaying the frame on the display, you now have this subframe latency. So it actually goes down to less than 10 milliseconds latency. And so now we can test this spatiotemporal offset that you get from MR, where you have a perspective offset and a time offset. And this is ongoing user study work, but we're hoping to come up with some actual guidelines for what are the tolerable levels of perspective and time offsets in MR that would then allow this to be usable as sort of the base replacement for AR, so that you just get this perfect view out to the real world. All right, so this is the end of that MR section. So let's pause again in case there's anything that you want to talk about.
Well, I love all of those. I love all of those prototypes, and I think that's a big reason why people should go to SIGGRAPH, because you show them there almost every year.
Yeah, so most of these that I'm talking about today, we have shown at SIGGRAPH, and that's our most common output for this is to share it with the SIGGRAPH community.
I love the Flamera headset, like the bug eye headset. It was such a smart idea. I was so impressed with that. And I think that's also the first time I met you and Grace.
That is,
actually.
yeah.
So
Yep.
was
Yeah, that was
awesome.
a fun project. And credit to Grace for coming up with a really creative optical design.
Do you have, because other companies have the same problems, do you talk to other researchers, or do other companies also share their research on this, on like how to do this? Because I know they also try to do perspective corrected views, like the Vision Pro, I think is quite good at that. I did some Vario headsets also have quite good correction. Do they use the same methods, or do you not know, or how does that work?
Yeah, I don't know. As far as I can tell, we're in a relatively unique position of being able to share these things to the community. And my perspective on that is that this list of problems that we have to solve is really big, and we need all the help that we can get. And if we want there to be a viable XR ecosystem that's out there in the world, like, we should all kind of work together to like solve these fundamental problems, so that it happens, period. So I am always pushing for, let's publish everything. Let's just get it out there, so that we can help get the momentum for the industry overall moving. But I don't see that as much from other companies. I don't have full visibility into it. Most of my visibility is specifically SIGGRAPH, because that's always where I'm focused, both on the publishing side and the volunteering side. And that happens to be where our team at least has the most presence. But I definitely consider myself lucky to be in an organization that supports that, to sort of take the longer term, broader view of trying to make this medium happen in the first place.
Yeah. So maybe completely different question. AI, like, how has AI influenced the way you do your research? If it has, like, do you use that to, I don't know, calculate the optimal position of the cameras, for example, or how do you use it?
More domain specific tasks, the less well existing tools work, and which makes sense, just because if the current AI revolution is really predicated on volumes of training data. Like, if you have just massive amounts of examples for something, it can build its model of what you're talking about. And the more down in the weeds you get, the more niche you get. It's just a matter of numbers. Like, there just isn't that much example material. Even if you take the corpus of all head-mounted display research papers, it's like probably only a few thousand pages. It's not like millions and millions and millions of pages of descriptions and text. And so I suspect that this is true for any specific subfield. You just can't. It doesn't know. That you have to really handhold the system to do what you need it to do. That said, I use it all the time for doing rapid prototype. Like, it is an amazing rapid prototyping tool, because a lot of the stuff that would be a time sink, anything that's as pedestrian as just like file management. Like, I generated all of these simulation renders in Blender, and now I need to move it into another format so I can process it. Like, being able to just say, hey, go do this, and it does it on its own, saves a huge amount of time. And that's on the the really basic stuff. But then when it comes to like plumbing up some parallel processing simulation engine, like, you can, if you have a clear mental model of what it is that you need to do, and you can break it down into subtasks that can be mapped onto problems where there is a lot of training data out on Stack Overflow or whatever, then you can also use it effectively. And so it's as a rapid prototyping tool, as important as like having 3D printers have been. It lets you do a lot more faster, even if the underlying philosophy behind large language models means that they don't really work that well for domain-specific knowledge.
Yeah,
Right.
yeah, that's
Interesting.
correct.
Cool. Let's talk about virtual reality. So we've talked about augmented reality, mixed reality, virtual reality, and this is kind of this progression of my own. Like the if you looked at the dates on the projects, they're a little bit out of order. But what I've organized this is my own progression of finding my way to like the core problems. And it started with AR and being like, AR is not really great for the visual experiences. Let's talk about mixed reality. And then I found that in mixed reality, there were lots of problems to solve, but they were all around just making it work, like sort of getting back to the point at which AR gives you in terms of the view of the real world works. And I was like, that's also not really the thing. It's like, if I just want to if I want to create capabilities so that artists can create new imagery, let's just do VR. Like, forget about all the other stuff. Like, forget about being able to have cooking instructions or whatever that you need access to the real world. Let's just say we're going to do just pure immersive content, and we want to address that. And that's where I've landed on. All right, this is the thing that I'm really motivated about. This is the problem space that I want to be working on. Let's do that. Now, of course, I have been working on this throughout the time, and because I'm always running multiple projects at the same time. So at the start, when I was doing that AR stuff, I also spun up an HDR project with my colleague Yang Zhao, who's here in this picture. He's an optical scientist, and we're both interested in image quality and HDR. And so we, as an exercise for ourselves, we re-implemented all of the major HDR display papers, but sort of reconfigured for eyepiece viewing rather than direct viewing. So the one that you're looking at here was a dual layer LCD module. Whoops, let's see, I went to the wrong slide. I've lost my mouse. Here's my mouse. There we go. Can you see this? No.
Yes.
There we go.
Yes.
So this is dual LCD modulation. So this is using two off-the-shelf LCDs that are stacked, and then they're aligned. And then, like you mentioned earlier, when we were looking at the mock-up of the AR display, you have one that dims down the backlight, and then the second one dims it down again, so that you get this additional contrast. The problem with this, with a normal LCD, is that LCD backlight is that you might end up with really good contrast, but then you have really low peak brightness. So the other configuration, which was one of the key papers out of Wolfgang Heydrich's group, is using a projector as the backlight. So the projector has a very bright source. It dims it down in the first stage, and then you have an LCD. It projects onto the back of the LCD as a backlight. And this is actually a pretty good way of creating high dynamic range images. It's just that it's bulky, and there's a lot of cooling issues because you have these big lamps that have to be cooled. But we were like, well, if this is the best way to do it from an image quality standpoint, let's actually just continue down this path. And so I actually picked this back up during 2020 and working in my little tiny home office, building this on my desk. And using like Amazon parts, basically. So I got a video light, and I got this 2 screens from resin 3D printers. So the UV printers that use an LCD to actually expose the resin. It turns out they're like very nice transparent LCDs that have very high contrast. And so I used 2 of those. So there's a very bright backlight, 2 of those, and then there's a Rift S lens that I just kind of stacked off on the top there. And this created a pretty functional near eye high dynamic range display that we could then repackage into something that is not head mounted, but head viewable display. So this thing is really big because of the heat issue. So the volume of it is almost 50% heat sink, and there are these big fans to draw the air through it to cool it down. The total weight is something like 3 kilograms. It's quite heavy. So the way that we actually showed this to people is we hung it from a like a tool balancer. It's a just a device that sort of you can set how much tension it pulls to
so it doesn't feel like 3 kilograms.
Yeah, exactly. And then you can still move around with it with sixed-off tracking, but you're sort of tethered to this point on the ceiling. And
it was also at SIGGRAPH, right? I
and we
remember
bought
this.
the SIGGRAPH, and we showed this demo where basically, so this is a low dynamic range video of the headset, so it doesn't quite convey it, but here it is in its normal operation. You can see it's like creating lens flares in the camera because it's actually really bright. If we stop down on the camera, you can see that the display is still creating these highlights. But if we go to low dynamic range mode, where we turn off the HDR capabilities, it gets clipped and you lose all this bright information that is there. And then we turn it back on, you get all that bright information. So this is kind of the best way in a low dynamic range video I can show it. This is really something that you just have to see by eye.
It was so bright.
Yeah, it's a really interesting thing to experience because it can recreate the full range of luminances you can get indoors. So up to the brightness of like an indoor light bulb, like ignoring windows and things like that.
It makes the whole experience like super realistic suddenly.
Yeah.
Right? It's
what
like
I found,
if you look.
What I found weird is that it's the image quality is low, like it was low resolution, and the lenses created all of these lens artifacts and whatnot. But it felt to me like you're looking at something real through a bunch of plastic, like through like a screen door and a plastic, but there's something real on the other side. I don't know if that was your if that was your experience.
It was. Yeah, that was exactly my experience. Like this sudden feeling of this looks so real in some way, in a way that like the normal headsets don't. It was really interesting.
Can you show it again? Because I really like.
Yeah, you can't see it. Yeah.
No, I do understand.
You can't really see it on a.
Yeah, but I like the light effects. It's.
Yeah, so it's interesting that those lens flares are real lens flares. They're being produced by both the lenses in the headset and the lenses in the camera.
Yeah.
But so like technically it is an image degradation. But when you look at it, and when you also still get those flares from the eyepieces and like your eyelashes and you can, like when it's really bright, you can actually feel the light like bouncing off of like your skin into your eye, and all of those things which are technically image degradations make it feel more realistic, just because it's like, well, that's how it's actually bright, like that's actually how light bounces around off stuff in the real world. And that it was surprising to me because I was like, the image quality is going to be bad, so maybe this isn't going to really show the effect. And it was like, no, actually the benefits are almost independent from image quality of having high brightness and contrast.
It feels like even if you're part of a movie or something, it's incredible.
Yeah, and then of course you should see it in real life because it's a totally different experience.
I understand. I need to go to SIGGRAPH at some point.
I have a question about this. About did you have any issues with distortion, with like aligning all of those optical elements? Or did you just like stack them really close together? Because that was like 20 years ago. I was like at university doing some stuff with high dynamic displays and projectors, and that was like a huge problem back then. That there was so much, like if there was like a light path between those elements, you would get huge distortion. I had to correct for that, and it was a big problem. So, yeah.
Yes. So we got around this in one way from an architectural standpoint, which is that we sandwiched the two LCDs like directly touching each other. They were like actually now the cover glass still meant that they were about 1.5 millimeters apart from each other. So there was some, and then with the magnification of the lenses, that means one pixel grid was like slightly offset from the other pixel grid. So we did have to go through a display to display calibration process that was not perfect because you had this slight offset between pixels. And then, and what happens is even once you get it aligned digitally, now you get a moire pattern because you have these like slightly different periods of repeating pixel grids.
Right.
And so the way that we did that, we've worked around that was we just put a diffuser after the last layer. So just blur it a little bit until it goes away. And in this case, that's okay because the LCDs were relatively low resolution. So it wasn't much, it was already low resolution, and the blurring, while it can get rid of the moire pattern, doesn't necessarily reduce your overall resolution that much. But that is a large problem. Like to do this properly, what you have to do is at the LCD manufacturing stage, put the two layers together with like a super thin cover glass in between the two, or not. It's not a cover glass at that point, but a substrate in between the two, which would be, a huge NRE cost, and it's not the kind of thing you would do at this prototyping stage. But that's not really the real problem here. The real problem here is that there's 120 watts of power and a bunch of fans and heat sinks on this. That's really why you can't do this for anything other than user studies. It's like the power requirements are just not sustainable.
120 watts.
120 watts.
That's a lot for a headset.
Exactly. Yeah. So that's the real problem. None of these other things are actually problems. But
no, but it's the fact that you can leave everything behind, that you don't have to watch the max you can actually go, allows you to be freely experimenting like this.
Yeah. I think it's that's really important strategically.
I agree, because otherwise you can't come up with these kind of examples, because even if you look at the first part you showed, which was really bulky, like all the lenses behind each other in the light, if you were already constrained, that would actually be dismissed, like, okay, we're not going into that direction. Well, now you can actually go into the direction, and who knows how small it can get in the future.
Yeah.
And then this approach could be a very interesting approach to actually get that effect.
Yeah. And I think it's really important to see these things in context, like see it in a headset where there is content and you can look around. Because you might find out, actually, this doesn't, if we had looked at this and it was like, it doesn't really feel like much, it doesn't help much, then that's also useful. Then not to spend more time on it. In this case, it was very much in the other direction. It was like, no, this actually really changes the experience. We should try to do this. But in either case, if you are just doing it on paper or even on a benchtop that's not fully in context of a headset, you don't actually know. You don't get that intuitive sense of like, this is something we should do or not do.
No, I agree.
And I think it's important to build. Okay. So on seeing this HDR headset, I had that simple scene with the two balls. I just made it in Unity, and I was like, you know what? Okay, we need to see more than these simple test scenes. Like this is compelling enough of a visual experience that we need to match the investment in the actual content that we're showing to the investment that we're making in the prototyping stage, so that we're prototyping the hardware and the software together. Like that's always sort of the approach that we've taken, but because we are a hardware prototyping team, we naturally spend more time on the hardware side of things. And I was like, you know what, we should just get some artists to work on this exact thing. So we hired the artist G-Monk, who's a visual artist who's done a lot of film work and also a lot of HDR photography work, lighting installations. He's a multimedia artist that has done a lot of stuff that I felt would be well suited towards, like, the skills that he has and his creative vision would be well suited to creating something for an HDR display. And so he made this triptych of 3 HDR environments for us as a little sort of ambient art piece. And we took that and exhibited it at SIGGRAPH. So it was this sort of, it was at Emerging Technologies, but it was sort of like an art gallery piece combined with an emerging technologies piece, because we had this new technical capability that we were showing and this an artistic creation that was created for it. So I this was a really rewarding process, because it was like, okay, now we're actually connecting these things together that I think fundamentally need to be connected in the development process. And unsurprisingly, like, people love seeing it. People love to have the demo not just be a tech demo, but it be an experiential demo at the same time. And having both of those two things together really tells the story better, I think, than you can get otherwise. So now, like, roughly a decade into working on this hardware research, I've grabbed onto this, and my core focus really is doing experiential development and hardware prototyping together, and having kind of a unified strategy between the two, so that we make sure that we're always working towards hardware that supports immersive media experiences, rather than going like down the path of hardware and then finding out that we've created something that isn't useful to artists, or maybe it doesn't have the right emphasis on different capabilities. If you kind of work at these things together, the immersive media side and the hardware development side, I think you stay closer to the path that gets you where you eventually want to go. And it's been of course very lucky to have the opportunity to make these choices and to do this kind of work, and to eventually have this realization that the foundation for me is creating a sense of wonder for people in the future. So that's my summary. Let's chat about any dangling topic.
Oh, thank you. Yeah, thank you so much. I'm definitely left with a sense of wonder after this presentation.
But I'm still rethinking everything I saw.
Right, but I already have a question, and that is, well, you work on all of those experimental ideas. How do you? And I mean, I assume the goal long term is to get some of those into production or into like production headsets. How does that process look like? How do you decide which of those ideas are actually pursued longer term? How does the research transition into production? Like, are you involved in that process? Is that a different team? Can you talk about that?
I would say I don't think it's an active process, at least the way that I conceive of it. It's that my job is to develop, is to map out the space of possible technical directions we could take and prove them out so that we understand what is our menu of options that we have. And in my personal focus is what are the menu of options that we have for visual immersive experiences. And research in general is building out this creating new candidate technologies or proving out existing candidate technologies or combinations of candidate technologies. And then, this is again my personal opinion about the way that research should work. But then a product team, a product manager, has some idea about where the market is, what users want, what the business opportunities are, and then they can pick from this menu of capabilities and say, this fits this market, this has this potential for this business case, and that is a separate discipline from making the menu in the first place.
Yeah, and I think that's also the part when you get into those limitations again. Because to create an actual product which is going to be used by consumers or companies, it needs to, you need to address.
Like if you take any of one of these things and you start going through the bill of materials, it's like none of these prototypes are viable
no.
in any way.
It depends, but I don't see people going to wear headsets with more than 100 watts on their head.
Yeah, exactly. Yeah,
that would be actually a hazard risk or something after some time.
Yeah, but in the same vein of looking at a particular capability and ignoring other constraints, I think it's also important to not consider business consideration, like to not take the cost, like the bill of materials, to not look at manufacturing, manufacturing readiness. That's in the same bucket for me as I'm thinking about resolution, so I'm going to ignore field of view, right?
It's not your problem. Yeah,
it's external constraint on the topic at hand.
So,
no, Alexander.
Yeah, I'm just curious because I saw so many things. What is the next thing you're working on? Are you allowed to talk about something, or?
All right, so I have queued up a teaser, which I can talk about very briefly.
I'm just curious.
So let's if you can bring my screen back up again. So I accidentally flipped to this earlier. You might have seen it briefly. So this is
a light stage,
an immersive media project. Whoop! Let's play it again.
Oh no!
Let's try it again. There it is. Can you see it?
Yes.
So this is just a short clip, but so this is a camera array that I borrowed from another team, and this is actually last year. Used it to shoot some test footage for an immersive media project that is. So as I mentioned, I'm like I'm balancing my project portfolio so that we're matching the immersive media side to the hardware development side more intentionally, rather than having that be an afterthought. And so I'm doing putting much stronger emphasis on volumetric capture to the work that I'm doing in the coming years.
Oh, nice. I see it has something to do with dance music. If I saw it right, it's like a DJ going wild.
Yeah.
Cool.
Are you capturing the volume, or are you also capturing, like, for relighting, for example? Are you also doing that?
I guess we'll find out soon enough.
I don't think he's allowed to say too much.
Yeah.
So, so then I have another question, like in your work or in general, because you do a lot with emerging technologies at work and outside of work.
Mhm.
Is there anything, a new technology maybe, or some research where you would say this is like super exciting and we don't talk about it enough?
Oh, yes, definitely. So there's a large portion of my portfolio that I did not include in this talk because it has not generated any headsets yet, is holography. So if you map out all of the sort of display technologies, you end up with like a lens in front of an LCD is the simple one. And then you get, more complicated stuff. And at the other end is always for 75 years or what, 75 years is holography, where you control at the wavelength level how light has constructive and destructive interference to create an exact replica, or as close of an exact replica as you can, to the complex wavefront that actually is going into your pupil from the real world. This is a much harder problem in many ways, but it is kind of the logical conclusion to the display system roadmap, that if you just look at all the way, like you want to be able to create perfect spatially varying focus, like holography, that's ultimately the way to do it. You want to be able to have very high contrast within the scene and very efficiently distribute the light, so that you're not throwing away light like you would with a backlight. Well, that's also probably holography. We want to make a really compact form factor that doesn't have a bunch of lenses. It's maybe just one element that's in a glass's shape. That's probably holography. Like everything always points to holography, but because it has been limited by compute capabilities and the capabilities of the actual spatial light modulators, or whatever you're using to perturb the light, has been limited, and more fundamentally by the number of people working on it. Because before this big last decade of interest in near eye displays, there was not a large scale consumer application for it. That there is a lot of work to be done to actually prove that technology out. Like everybody has an idea that like the capabilities are probably there to address all of these things, but we have to actually figure out how to do it. So I've been working on a number of projects, many of which are already published. I just didn't talk about them here because they're much more theoretical and they don't have the hardware prototypes. Well, they have hardware prototypes, but it's just a bunch of components on an optical table. In all of these cases.
Interesting. Maybe you can give a short summary. How little I understand of it from holography is like that, like calculating like the diffraction grating that you need for every single image is like super computationally intensive. So doing that for every frame is a huge amount of computational power. That's what I know about it. Do you think the solution is like towards more compute power with, I don't know, quantum computers or AI, or what direction are you thinking of?
Yeah. So we mostly just ignore compute, but even if you have all the compute in the world currently, it's not possible to create a good image. Current holographic capabilities have very limited étendue, which means like you either have a small field of view or you have a very small eye box, like you lose the image if you move slightly. They have high noise, like very poor SNR, due to speckle, like uncontrolled interference that happens with the in the image formation creates noise. They are currently bulky, even though in theory they could be made small, because the capabilities of the modulators themselves require a bunch of additional optics to prepare the illumination beam and then magnify it afterwards, and so they actually end up being quite bulky currently. So ignoring compute completely, we have to tick off all of these. So like that list of problems that I had at the beginning, there's a whole other list of problems for holography that currently exists, and we've taken some steps to lately we've been doing a lot of work just to reduce the speckle, to reduce the noise in the image.
Right.
My colleague Grace, who did the light field pass-through project, has mostly worked on holography, including Eitan-Du expansion, so making larger fields of view possible. We've done some work to try to move towards making dynamic images possible, so using faster modulators. There's basically two major types of commercially available spatial light modulators that can adjust the phase of light on a pixelated basis. One of them is basically just an LCD, and by changing the state of the liquid crystal, you delay the light more or less. The other option is a variation on the MEMS technology that's in a DMD projector. So those projectors have little mirrors that flip up and down to turn the light on and off. You can construct them to, instead of flipping up and down, to actually sort of piston up and down and introduce a phase delay that way. Those ones can operate much faster, in the same way that the DMD projectors can operate much faster than an LCD. That lets you just create more images more quickly, which has some consequences on the interactive capabilities of it, as well as noise reduction and other things. So we've done a bunch of these things, but it's very much the early steps out in individual directions on the list of things. Eventually those will go towards headsets that do demonstrate, here is a new capability like we've done in the past, but we haven't gotten there yet. So far it's just been SIGGRAPH papers.
Awesome. Well, thank you. Well, thank you so much. That's there's so many topics now that I want to read about, and I'm sure Alexander too, and hopefully everybody watching as well.
Yeah.
And
there is a lot of information. I need to deep dive in some of these things again. I didn't. The funny thing is, we use headsets like HoloLens, like Vision Pro, Snap Spectacles, Meta Quest's VR headset, and you don't think about what's going on. You do know a little bit about the technology of how it works, but you do not expect there is so much research behind these things actually to get to a point that it's getting better and better. It's always funny. I've seen it in my period with HoloLens, where HoloLens 2 came out and people were again complaining about the field of view or something else, but not understanding what it takes to actually have something running for at least 3-4 hours and able to produce what it actually was doing.
So much of these challenges come down to just power. All of it, getting enough power is the hardest thing.
Power is indeed the hardest thing. Thanks, Nathan. I really love this. Thank you so much.
Thank you very much. I really enjoyed getting to talk about these topics with both of you. It's always fun to talk about.
No, it's really great.
Shall we round up?
Yes. I think there was a very interesting, very long session.
Normally the session's around 30 minutes, but we are now at almost 1.5 hours. I don't think anyone is going to complain, to be honest, because I'm not even. So thanks again, Nathan, for this really great session and the ability to ask questions and have a discussion.
Maybe before we finish, where can people find you if they want to see more about your research or get in contact? Or
so the best way to reach me is via Instagram. So my handle is just Nathan Matsuda, all one word, no spaces. You can also reach me pretty reliably on LinkedIn. It's also Nathan Matsuda is also my handle there. But please reach out if you're interested. And otherwise, come find me at SIGGRAPH.
Awesome. Well, thank you so much, Nathan. That has been great. And
thank you. Really appreciate
everyone.
Okay.
Thanks for watching. And see you next time. Bye.